All right, so we're going to start sort of developing our way to do proofs. So we're starting to get into the area of geometry where we're going to be doing some proof writing. And this is the logical piece, the logical thinking, the logical process to geometry, that logical portion of it. And we've been doing some building blocks for this already. Trying to find conclusions and ways to get to conclusions and things like that. So that's what we're going to talk about today. Um, and so we start with going back to algebra class a little bit. You've done proofs before in algebra. They were algebraic proofs. And so we'll bring those back as a way to sort of transition into writing geometric proofs, which are going to look very different. So a quick reminder, in your algebraic proofs, you used algebra properties to justify how you solved an equation, right? The addition, subtraction, multiplication, and division properties, all of which say that you can add the same number to both sides of an equation, you can subtract the same number from both sides of an equation, you can multiply the same number to both sides of an equation, or, we'll see in a second, you can divide the same number to both sides of an equation. And when you do that, you do not change the meaning of the equation. You just create what we call an equivalent equation. So every time you add 5 to both sides, then you justify doing that with the addition property. Makes sense. And there's the division property, which says that we can divide anything we want into both sides of an equation, except, of course, for 0. Can't divide by 0. Well, you also use the substitution property, which says that if A is equal to B, then A can be substituted for B anywhere else. Or a better example is if X is equal to 4, then what we knew is we could take 4 and substitute it in for X anywhere else we wanted to. We've actually done that in this class. And then your distributive property, which says if you have a number sitting outside of a set of parentheses, you can distribute that, or not a number, but anything, any term sitting outside a set of parentheses, you can distribute that term to inside the parentheses, and when we distribute, we multiply. Okay? So those are the properties that we're going to use to justify our algebraic proof. Now, going back to class, algebra class, we even then started, and we'll keep using in this class, 2-column proofs. One column was for our statements, and the other column was our reasons for doing so. And so what a proof is, it's taking a piece of information, trying to reach a conclusion through a series of steps, and all along the way you're trying to make a good argument. And in order to make a good argument, you need to have a reason to back up what you say. You need to go clean your room. Why? Because I said so. This is not a great reason. You need to go clean your room. Why? Well, because if you don't, you leave dirty dishes and dirty clothes and stuff laying around, you start getting bugs and rats and mice and all that kind of stuff. It's a little bit better reason to maybe provide a little bit more motivation for you to go clean your room. So we need good reasons to back up our statements. Okay? And so we started here in algebra class where you're given some equation. And in any proof, that's where you start, right? You can't really start a proof unless you have some given information. This is what we know. This is what we're going to start with. And this is where we want to end up. And so we have a given equation, and we want to walk our way all the way down to where we know that X is equal to 2. Well, how in the world do we get from this big equation down to X equals 2? Well, through a series of steps. And so we start. We write down our equation first. And how do we know to write that down? How did we get to where we wanted to write that down as a statement? Well, that was given to us. And so we start with given. Always your proofs start with given. Now, with algebraic proofs, it's pretty easy to come up with the next statement because you're just solving the equation. What would you do first to solve this guy? Well, hopefully you're saying you would distribute. So we're going to distribute the 3 and the 2, and we end up with 6x plus 3 plus 4x plus 2 plus 7 equals 42 minus 5x. Now, why do we get to do that? What reason do we have for doing that? And the distributive property says that we can do that and not change the equation. So we're using the distributive property. Okay, what would you do next to solve this equation? Well, we're going to combine like terms, right? So 10x, 3, 2, and 7 gives you 12. And there's not a property for that. What we're doing is we're combining like terms. So we can just call it combine like terms. Now, you'll also see it as just simplifying. So simplify. That works too because we're just simplifying the equation. But we're combining like terms, so we can call it that. Choose either one. You don't have to write both. Choose either one and go with it. My guess is you're going to choose simplify, and that's okay. All right, back to our equation. What would you do next to solve? Okay, and hopefully you're saying that I would add 5x. Now you have to show this. That's the excruciatingly painful part of doing an algebraic proof. You've got to show adding 5x to both sides. And we're allowed to do that because the addition property says that you can add something to both sides of an equation as long as it's the same thing. You don't change it. Okay, and then we got to actually do it. So we get 15x plus 12 equals 42. And again, we're combining like terms. Or simplify again, you can do that. Okay. Next step you would take would be subtract 12 from both sides, right? And again, we're showing that. We have to have a reason for doing that. Since we're subtracting, it's going to be the subtraction property that we're using. Okay, then we're going to actually do that. We get 15x, so this is going to add to 0, and we get 30. And again, we're combining like terms or simplify. So I'm going to keep writing both. You just choose one that makes the most sense to you and use it. Okay, the last thing we're going to do to solve this thing is divide both sides by 15. And that's from the division property. And then from there, it's kind of odd to think about combining like terms when you're dividing 30 by 15. So I think it makes more sense to go ahead and just call this step simplify. Because you're not really combining like terms. It's weird to think of it that way. So, and there we go. We've gone from that original equation down to x equals 2, and there's all the steps that we used to get there. And justifications for why we got to do it. What made it okay. Okay? That's how we do our algebraic proofs. So you got one here. Think about this one for a second. Plan it out. We've got some statements here, reasons here. And what you may find is that it's easier to just solve the equation on the left-hand side first and then fill in your reasons. And while I'm at it, well, yeah, that's it. So maybe solve the equation first. So think about that. What are you going to do first, then second, then third, and then you're going to be done. So I'm going to go ahead and do that. Solve the equation. We're going to add x. So we get 3x plus 3 equals 9. Then we're going to subtract 3. Then divide 3. And look at that, x equals 2 again. Now, every step you made, you have to have a reason. So here, we started with the equation because it was given to us. Then we added x to both sides, and the addition property says that we're allowed to do that. And then when we actually combine those x's, right, we were simplifying or combine like terms. Then we subtract 3 from both sides. That was with the subtraction property. Then we combine like terms again. Then we use the division property to divide by 3. And then we simplified 2 to x equals 2. Okay? And there you go. Making enough sense? I hope so. You got one more. Give this one a shot. You can stop the video, write it all out. Statements and reasons. Whichever method you like better. If you want to solve the equation first and then fill in your reasons, that's fine. Or if you want to do the reasons as you go, that's fine too. But you stop the video, and then when you're done, start it back up and see how you did. And there you go. That's what it should look like. All those steps need to be included. If we give you the number of steps, then you can be assured that you need to use all those steps. So every single step needs to be shown. You need to use all those lines, all those boxes. Okay? All right. Now, we're going to continue to build on reasons we get to do things. There's some more properties to talk about, like the reflexive property. The reflexive property seems fairly obvious. Actually, a lot of these properties do. But we need to understand that we can, all these do, but we need to understand that we can use these properties to help us write statements in our proof. So, for example, first, reflexive property. Reflexive property is kind of like you standing in front of a mirror and seeing your own reflection. Because the reflexive property is what says that something is equal to itself, which is incredibly obvious. A is, of course, equal to A in an algebraic setting. In a geometric setting, the length of AB is equal to the length of AB, or the measure of angle A equals the measure of angle A. But we can also transfer this into a congruence statement and say that AB is congruent to AB. And there are times where we're going to want to use this idea to come up with a statement in our proofs. Same thing for angles. Angle A is congruent to angle A. Okay, that's one. Next property is the symmetric property, which says that something is equal on both sides. It's the same on both sides. And so in an algebraic setting, that looks like if A is equal to B, then B is equal to A, and that makes sense. That's what allowed, when you're in algebra class, that's what allowed your algebra teacher to say that -4 equals x, and when you said, the way I got x equals -4, that's the same thing, right? And so in geometry, if the length of AB is equal to the length of CD, then the length of CD is equal to the length of AB. Even more so in terms of figures, we talk about figures being congruent, it works there also. AB is congruent to CD is the same thing as saying that segment CD is congruent to segment AB. And again, there are times where we're going to want to be able to do that. And it works for angles as well. If angle A is congruent to angle B, then we can say that angle B is congruent to angle A. Okay? And the last one is the transitive property. The transitive property sort of transfers equalness, which is not a word, but whatever. In other words, it kind of looks like the law of syllogism in our deductive reasoning, but the transitive property says that A is equal to B and B is equal to C, then we can say that A is equal to C. We're going to go through B and cut out the middleman and say that A is equal to C. And same thing with segments and angles. If segment AB is, the length of AB is equal to the length of CD, and the length of CD is equal to the length of EF, then we can say that the length of AB is equal to the length of EF. And again, in geometric terms, where we'll normally most often talk about the segments being congruent, it still works that way because it works that way for the measures. The same thing for the angles. angle A is congruent to angle B, and angle B is congruent to angle C, then of course angle A is going to be congruent to angle C. Okay? We're transferring that congruence through a middleman. Okay? There are not just properties. We're allowed to use other things as reasons to support your proof. Properties are going to be a big one. We're also allowed to use definitions. Any definition that we get to in this class, you can use as a reason to write a statement. Theorems. Theorems are the geometric rules that we have to prove, but once we've proven them, then we get to use them in our proofs to help write statements. These are all things that we're going to do to try to help to write statements. Corollaries are just amendments to proofs. They're more specific examples, of theorems, amendments of theorems. They're more specific examples of those theorems. We can use those too. And then postulates. We've talked about postulates, those rules that are just accepted as being true without proof. We can use those to help us write statements. And the last thing I'll say is that we can use a diagram. There are some things we get to assume from a diagram, as long as it's marked properly, that we can use to help write statements. Okay? And so an example of a geometric proof is here. Okay? What you're going to find is that it's tougher to figure out what statements to write in a geometric proof than in an algebraic proof. You're not necessarily solving an equation. But it's the same idea. So we're going to start with some given information, and right now our given information is all in this picture right here. Very often it'll just be written down. Here's what we're going to give to you. So from that diagram, we need to prove that the length of CF is equal to the length of AD. Well, it may be tough to see that with that diagram, where those pieces are congruent, how CF and AD are going to be equal. But that's the nature of our proof. We're going to show that link through a series of statements and reasons. Okay? So, let's go. How do we know, in this first statement, how do we know that AB is equal to, something? Well, AB is equal to something because of the tick mark there. AB is equal to EF. And that was given to us. We're getting it from the diagram. And the diagram was given to us, so that was given to us. Same thing with BC. BC is equal to DE, and that was given to us. Now, our next statement, the statement we're going to write, will either come from the diagram, it will come from a definition, theorem, corollary, postulate, property. Or it might come from the statements that we wrote down before it. Okay, here, this one's going to come from the picture. This says that AC, which is right here, is equal to AB plus BC. What says that? How do we know that that's true? Well, the segment addition postulate says that that's true. So that's what we're going to use to say that. It's the segment addition postulate. Okay. Well, same thing for DF. If you look at DF, right, DE plus EF would help get DF. That's the segment addition postulate, which is what we're suggesting, suggested to use. So EF plus DE. Right? Now, look here. Here's what I mean about using the statements from before. How do we get from this guy to this guy? Well, we've replaced EF with AB and DE with BC. And these two statements say that that's okay. Since AB and EF are equal, I can put an AB in anywhere I see EF. And the same for BC and DE. Why? Well, we just saw that property. It was the substitution property. Okay. Now we've got this statement. We know that AB and BC, AB plus BC is equal to AC. So we're going to let AC, we're going to substitute AC in for that. So DF is going to be equal to AC. And again, that's from the substitution property. Okay. Now, we know that DF is equal to AC, and now we're going to add CD to both sides. That's just the addition property. We're allowed to do that. The addition property says you can add the same number to both sides and not change the equation. Okay, and then we're going to use the fact that DF plus CD, okay, DF plus CD is equal to CF. Well, that's your segment addition property again. It's coming back. Not property, postulate, sorry. Segment addition postulate says that's true. And then the same thing for AC and CD. AC plus CD is going to be equal to AD. And that's by the segment addition property. The segment addition postulate. Keep saying property. Okay. Now, combine some steps again. CD plus DF is equal to CF. So I'm going to put CF in for this DF plus CD. AC plus CD is equal to AD. So I'm going to take this AD and I'm going to substitute it in to this guy right here. So I'm going to say that CF is equal to AD, and that's by substitution. And that's what we wanted to prove. We wanted to prove that CF was equal to AD. Okay? So your first sort of introduction into a geometric proof. The toughest part with these guys is going to be, where am I coming up with these statements? And we're going to have to start getting pretty good, developing some strategies, using pictures, using theorems, definitions, corollaries, postulates, properties, anything that we can to write a statement. And then try to follow that statement down to what we want to prove. It's going to be tough, but we'll get through it. Okay? That's it. Homework's out in Canvas. Make sure you have that done by next time.